Good evening, everyone. So today this will be the last lecture related to the current electricity. And in this lecture, we'll be discussing some of the miscellaneous questions, right, that are asked from this chapter, right? We'll be discussing some problem solving or some of the problems, very important problems with respect to this chapter. And then we'll be starting with the magnetism, right? So let's start with the problem discussion here. The problem number 1 here on the screen is a uniform wire of resistance 8 ohm, right? We have a uniform wire, right, of resistance 8 ohm. It has been bent in the form of a circle, right? Which means that suppose we have this uniform wire, right? This is the uniform wire of some length L, and it has got some area of cross section A, right? This is a wire of length L, and it has got some area of cross section A. Now what we do is that we just bent this wire of length L into a circle, right? Into a circle, right? We have formed a circle like this shown in the figure, right? So we have bent this wire in the form of length, right? In the form of circle, right? So it means that whatever be the length of this wire, right? Same will be the circumference for this circle as well, right? The total resistance for this wire has been given as 18 ohms, right? It means the total resistance of this circular wire will also be 18 ohms, right? The total resistance, if we talk about the total resistance of this wire which has been bent in the form of circle, will also be equal to 18 ohms, right? But the question is that we have to calculate the effective resistance across the points between A and B. You can see in this picture, we have 2 points here, A and B, right? We have 2 points here, A and B. A and B are the 2 points here, right? A and B are the 2 points here. So we have to calculate the total effective resistance between these 2 points A and B, right? Between these 2 points A and B. You can see that the total resistance of this wire is 18 ohms, right? And this angle here has been given as 60 degrees, right? 60 degrees, right? 60 degrees. It means that the 18 ohm actually has been distributed along the whole circumference of this circle, or we can say 18 ohm resistance actually corresponds to 360 degrees of angle, right? 360 degrees of angle. And we will try to calculate for this angle theta equal to 60 degree, how much resistance will be there between point A and B, which subtends an angle of 60 degree at the center of the circle, right? At the center of the circle, that's at point C, right? That's at point C. So the resistance per degree angle will be equal to, actually, that will be for 1 degree, the resistance will be 18 upon 360, right? And similarly for 60 degree angle subtension, the angle resistance will be equal to 18 upon 360 multiplied with the 60 degree, right, multiplied by the 60 degree. So it will be 18 upon 6. It will be 18 upon 6, right? That's equal to 3 ohms. That's equal to 3 ohms, right? It means that from A to B, the resistance is from A to B, the resistance is actually 3 ohms, right? And the remaining resistance will be from B to A. The remaining resistance will be from B to A. Since the total resistance is 18 ohm, so rest part of the circle is going to have a resistance of equal to 12 ohms, right? Resistance of equal to 12 ohms, right? So 12 ohm will be the resistance for rest part of this circle, right? So it will be 3 ohms here, right? Not 12 ohms. It will be left with 15 ohms, right? It will be left with 15 ohms. That's 18 minus 3. That will be 15 ohms. So rest part of this circle will be having a resistance of 15 ohms. It means that between A and B, this is the point A and this is the point B. We have one resistance that's of 3 ohms like this, right? And we have another resistance of 15 ohms like this, right? 15 ohms like this. So this is 3 ohm resistor and this is 15 ohm resistor, right? And we have to calculate the effective resistance between these 2 points. You can see that now the 3 ohm resistor and the 15 ohm resistor are now in parallel to each other. They are in parallel to each other. So it's a parallel combination of the resistances. The effective resistance, R effective, will be nothing. It will be the effective resistance for the two resistors is actually R1 into R2 upon R1 plus R2, right? So it will be equal to 3 multiplied by 50 upon 18, right? Upon 18. So it will be 3, 6, right? Or it will be 5 upon 2, right? That's equal to 2.5 ohms. 2.5 ohms. It means the effective resistance for this question between the points A and B will be equal to actually equal to 2.5 ohms, right? Or 5 upon 2 ohms, right? So this will be the effective resistance. This will be the effective resistance between the points A and B, right? So let's move on to the next question. The similar type of question we have with respect to the resistances here. The question is that calculate effective resistance across the points A and B, right? Across the points A and B. So it means that we have to calculate the effective resistance between the points A and B, right? This is the point A here, right? And this is the point B, right? It means if we have to calculate the effective resistance between points A and B, we have to connect a battery between the points A and B, right? This is the resistor R, right? And this is our point A here, and this is our point B, right? We can see that all the four resistances are having the common point here, right? That's this point. This is the common point for all the resistors, right? So it means that for all the resistors here, the potential at this point will be same. So they will be at same potential. This end of all the resistors will be at the same potential because they are connected at the common point, that's the center of the circle. But you can also see that the other end of the resistors is actually connected to the circumference of the circle. It means that actually the other end of these resistors is also connected to each other, right? They are also connected to the same point, right? It means that what will be the potential of this point, same will be the potential of this point, and same will be the potential of this point as well, and the same will be the potential at this point as well. It means that the potential difference across all these resistors is actually same, right? If the potential difference across all these resistors is actually same, it means that we can say that all the four resistors here are actually in a parallel combination, right? They are in a parallel combination. It means we can place all the four resistors in a parallel combination like this, right? So this is resistance R, this is R, and this is also R, and this is also R, right? So these are actually the four resistors or the four resistances which are actually in a parallel condition or in a parallel combination. And we know that in case of parallel combination of resistors, we have R effective as 1 upon R1 plus 1 upon R2, right? Plus 1 upon R3 plus 1 upon R4, right? So that will be equal to, for this case, that's 1 upon R plus 1 upon R plus 1 upon R. So it has to be reciprocal of R effective, right? 1 upon R effective plus 1 upon R. So it will be actually equal to 4 upon R, right? Or our effective resistance, R effective will be actually equal to R upon 4. So this will be the effective resistance for this circuit, right? So for this circuit, or for this diagram here, for this arrangement of the resistors, the effective resistance is actually equal to R upon 4, right? Let's try to discuss the similar type of question. That's the question number 3, right? Question number 3. You can see in this question, question number 3, a wire of resistance 6 pi ohms per meter, right? We have some wire, right? There is a wire like this. Let's suppose from A to B, we have this wire. A to B, from A to B, we have a wire, right? From A to B, we have a wire. Let's suppose the length of this wire is actually L, right? And the radius of this wire is given as 1 meter, right? Is meant to form a circular loop, is meant to form a circular loop, right? And thus the radius of this circular loop is actually given as R is equal to 1 meter, right? R is actually the radius of this circular loop. That's equal to 1 meter, right? And the question is to find equivalent resistance of the loop between diametrically opposite points. So diametrically opposite points for this circular loop are the 2 points A and B, and about these 2 points we have to find the effective resistance or the equivalent resistance for the this circular loop of wire, right? So it's given that a wire of resistance 6 pi ohm per meter, right? A wire of resistance 6 pi ohm per meter. So it's resistance per unit length, right? So if the resistance per unit length is 6 pi ohms, right, per meter, right, then the total resistance has to be total resistance. Then the total resistance will be equal to the total length, right? The total length multiplied by the resistance per meter, right? That will be the total resistance. But the total length of this wire is the same, actually the circumference of this circular loop, right? So the L has to be equal to 2 pi r, that's the circumference of this circular loop, right? So this L has to be actually equal to r is given as 1 meter, so this L has to be equal to 2 pi, right? It will be 2 pi meter. So it means that total resistance now will be total resistance will be equal to 6 pi multiplied by this 2 pi, right? 2 pi. That will be equal to 12 pi square. 12 pi square ohms will be the total resistance for this wire of length L, or for this circular loop of circumference 2 pi, right? 2 pi. So this is the total resistance, right? Now between A and P we have this semicircle here, right? This is a upper semicircle, right? And then we have lower semicircular part, right? So it means that for upper half of the circle, the resistance will be half of the total resistance, right? Half of the total resistance. So half of the total resistance will be 2 pi square upon 2. That will be equal to 6 pi square, right? It will be 6 pi square, right? And lower half will also have the resistance equal to 6 pi square. And you can see that we can just replace the upper half of the circle and lower half of the circle with the resistors, right? Right? And there's a common point A and P, right? A and P is the common point, A and P. So the resistance of half of the circle is 6 pi square and lower half of the circle is 6 pi square, right? So their effective resistance will be nothing. R effective will be equal to R1 multiplied by R2 upon R1 plus R2, right? That will be actually equal to 6 pi square multiplied by 6 pi square, right? Divided by 2 times 6 pi square, right? So it will get cancelled. So we'll be left with R effective as R effective will be actually equal to 3 pi square, right? It will be 3 pi square. So pi square has the value approximately equal to 10. We can say that its effective resistance will be almost equal to 30 ohms, right? 30 ohms, right? So 30 ohms will be the approximate resistance for this combination of resistors, right? Now let's discuss one of the important topics, right? From the previous chapters that we discussed, we had a discussion on it also. Let's try to quantify this term, right? That's the temperature dependence of resistivity and resistance. In the previous lectures, we discussed that actually the resistance is of a conductor is given by rho L upon A, right? Rho L upon A, where rho is the resistivity of a conductor, right? Rho is the resistivity of a conductor, and L is the length of a conductor, correct? Rho is the resistivity of a conductor, L is the length of a conductor, and A is the area of cross section of a conductor, right? So we have two things here. One is the resistivity, another is length, another is area of cross section, right? So it means, let's suppose that we have this conductor of length L and area of cross section A. A is the area of cross section, right? A is the area of cross section, correct? So A is the area of cross section for this conductor. So L is the length of this conductor, or we can write this area of cross section as pi r square, right? Pi r square. So pi r square is nothing. It's actually the area of cross section for this conductor, right? So we know that temperature dependence, how the resistance actually depends upon the temperature, right? We know resistivity actually depends upon the temperature. Resistance also depends upon the temperature. And for conductors, we know that resistance or the resistivity increases, right? Resistivity increases or resistance increases upon increasing the temperature, right? So for conductors, resistance or resistivity, resistance or resistivity, resistance or resistivity increases, right? Increases on increasing temperature, right? On increasing temperature, right? So on increasing temperature of a conductor, resistivity as well as resistance increases, right? So it means that there must be some temperature dependence or some relation between the resistivity as a function of time or resistance as a function of temperature, right? Not time. So let's suppose at temperature T equal to T naught, right? Resistance is R naught, right? Resistance is R naught. Then at later temperature T, then at later temperature T, let me call that as R of T, right? That's the temperature, that's the resistance of a conductor at some later temperature T, right? So this R of T will be given as R of T will be nothing. It will be equal to, it will be R naught 1 plus alpha delta T, right? And this rho will be nothing. Rho of T will be nothing. It will be rho naught multiplied by 1 plus alpha delta T, right? So this is how the resistance and the resistivity of a conductor depends upon a temperature. So what is this delta T? Delta T is nothing. It's actually the change in temperature. That's T final minus T initial, right? What is alpha? It's called as coefficient of resistance, right? Or temperature coefficient of resistance, right? Temperature coefficient of resistance. Temperature coefficient of resistance. So it's actually called as temperature coefficient of resistance, right? So we can write this alpha actually as alpha will be delta R, right? Delta R upon R naught, right? Upon delta T. Or we can say, we can define it as it's the relative change in resistance per degree change in temperature, right? It's the relative change in resistance per degree change in temperature, right? So we can define it as relative change in resistance per degree increase in temperature, right? Increase in temperature. So it means that for each degree rise in the temperature, how much actually the relative resistance or the how much the resistance actually changes. That's defined by the this temperature coefficient of resistance, right? Temperature coefficient of resistance. So temperature of coefficient of resistance is nothing. It's actually the relative change in resistance per degree rise in temperature or per degree change in temperature, right? That's what we call as temperature coefficient of resistance, right? And we know for conductors, when the temperature increases, right? The temperature increases, the resistance increases, right? If resistance increases, delta R has to be positive, right? If resistance increases, delta R will be positive, and the temperature increases, delta T will be positive. It means alpha has to be positive for conductors. We can also see that if the temperature decreases for the conductors, delta R will be negative, right? And temperature decreases, then delta T will also be negative. Still, the alpha will be a positive quantity, right? It means that alpha is always positive quantity for conductors. And similarly for semiconductors, Upon increasing the temperature, the resistance decreases, right? If we increase the temperature in case of semiconductors, the resistance of semiconductors actually decreases, right? So delta R will be negative for the semiconductors and delta T will be positive. It means that for semiconductors, the temperature coefficient of resistance will be actually a negative quantity, right? So wherever alpha is positive, it will be actually a conductor, right? And where alpha is negative, it will be a semiconductor, right? For semiconductors, alpha is actually negative, right? So let's start with this basic question, right? The question here is here on the screen that the temperature coefficient of resistance for a wire is given as 0.00125 per degree centigrade, right? At 300 Kelvin, right? At 300 Kelvin, right? Its resistance is 1 ohm. So at 300 Kelvin, the resistance of a resistor or the conductor is given as 1 ohm. The temperature at which the resistance becomes 2 ohm is, we have to find the temperature, how much temperature we have to increase or decrease, right? Because the resistance here is increasing, right? So the temperature must increase to increase the resistance for a conductor, right? That means we have to find the new temperature at which the new resistance for this conductor will be equal to 2 ohm. So what we'll be doing is that we'll use the same equation, that is RT, that's the that's the resistance at some later temperature T, right? Plus alpha delta T, right? Alpha delta T. So this delta T will be nothing. It will be equal to T final. Let's call that as T minus T initial, right? T initial. T initial. So whether you take change in temperature in Kelvin Kelvin scale, or you take the change in temperature in degree scales, right? Or centigrade scales, the change will be the same for the same scale for both the scales, right? It doesn't matter whether you measure the temperature in Kelvin scale or you measure the temperature in centigrade scale. The change in the temperature will be the same for both the scales, right? So T minus Ti, initially it was given as 300 Kelvin, right? It will be T minus 300, right? T minus 300. So our initial resistance R naught was given as 1 ohm, right? It's 1 ohm. So the final resistance will be equal to 2 ohm, right? It's 2 ohm resistance. So 2 into 1 plus alpha delta T. Alpha is given as 0.00125 upon delta T. So delta T is nothing. It's T minus 300, right? So this is the equation. So from this equation, you can easily calculate. So our it will be equal to 1 plus 0.0125 upon T minus 300. That will be equal to 2, right? So from this equation, you can easily actually calculate how much there will be a change in temperature, right? Or you can write T minus 300. That will be equal to, okay, T minus 300 will be actually equal to, it will be 2 minus 1, that's 1, right? So 1 upon 0.00125, right? So our T will be actually 300 plus 1 upon 0.00125, right? So it means that let's recheck it. So R naught was 1 ohm, right? 1 plus alpha, alpha is given as 0.00125 per degree centigrade, right? Delta T, right? So delta T has to be multiplied here. We have divided the delta T here, right? So we cannot divide delta T here. It has to be multiplied, right? So delta T is actually, that's actually T minus 300, right? Delta T is nothing, it's T minus 300, right? So it will be equal to 1 plus 0.00125 T, right? T minus 0.00125 multiplied by 300, right? 300. And that's equal to 2, right? That's equal to 2, correct? So our temperature will be actually equal to 2 minus 1 will be 1. So it will be equal to 1 plus 0.00125 multiplied by 300, right, upon 0.00125. So this will be the final temperature in Kelvin scale, right? Which scale? Kelvin scale. So this will be the final temperature in Kelvin scale. Similarly, we have another question here. If the resistance of a conductor is given as 5 ohm at 50 degrees centigrade. So the resistance of a conductor is 5 ohm at 50 degrees centigrade and 7 ohm at 100 degrees centigrade. Then the temperature coefficient of resistance of the material is. So we'll use the same equation. R is equal to R naught 1 plus alpha delta T, right? So our delta T here is nothing, it's 100 minus 50, right? That's equal to 50, right? That's equal to 50. And our alpha is nothing, it's delta R upon delta T. Delta R here is 7 minus 5, right? 7 minus 5 upon R. R is the initial resistance at temperature 50 degrees centigrade, that's upon 5, right? And divided by delta T, that's 50, right? That's 50. So it will be 2 upon 250, right? 2 upon 250, or we can write it as 1 upon 125. That will be the alpha. This is the value of alpha. So 1 upon 125 is the value of alpha for this question. The temperature coefficient of resistance for this material will be actually 1 upon 125, right? And its units will be per degree centigrade, right? It will be per degree centigrade. Per degree centigrade. That will be the unit for temperature coefficient of resistance for a material, right? So let's see. Let's move on to the next question here. The question here is: a wire is stretched by 30% of its original, right? Find percentage increase in resistance, right? So it means that let's suppose we have a conductor of length L and some area of cross section A, right? And its resistance will be given by R is equal to rho L upon A, right? Rho L upon A. A wire is stretched by 30% of its original, right? 30% of its original. Find percentage increase in resistance, right? So if it is 30% stretched from its original, it means if it is initial length is L, then its final length has to be equal to 1.3 L, right? That will be the 30% increase in its length, right? And one of the important property upon stretching the wire is that the length of the wire changes, the area of cross section of this wire changes, but the thing that does not change is the volume of this wire, right? So volume, whatever be the volume initially, same will be the volume finally, right? So the initial volume has to be equal to the final volume for this wire, right? The only thing that will change, length is going to increase, but the area of cross section for this wire is going to decrease, or we can say the area of cross section for this wire will actually shrink and the length of this wire will actually increase, right? So now let's see what's going to happen with respect to the percentage change in resistance, right? So final resistance will be, let's call that RF. Since material has not changed, so the resistivity will not change, right? Length has become actually 1.3 times L, and area of cross section, we don't know what is the area of cross section. New area of cross section, we call it as A dash, right? And the volume initially is equal to volume final, and volume of this conductor will be given by initial volume was A, and the length of this initial area of cross section is A, and the length of this conductor is L. So A into L will be the initial volume, and the final volume will be L dash, right, multiplied by A dash. This is the final volume, right? And we know that L dash is nothing, is the final length, that's 1.3 L, 1.3 L multiplied by this A dash, right? Multiplied by this A dash. So L and L will get cancelled. So it means that A dash has to be actually equal to A upon 1.3, right? A upon 1.3. So this will be the new area of cross section for this. So the new resistance, the final resistance for this conductor will be actually rho times L into 1.3 upon A dash. The value of A dash is A upon 1.3. So it will be A multiplied by 1.3. So it will be rho L upon A. It will be 1.3 whole square, right? It will be 1.3 whole square, right? Now, we have to calculate the percentage change in the resistance, percentage increase in the resistance. So percentage increase in the resistance will be nothing. It will be delta R upon R multiplied by 100, right? Let's first calculate this. So delta R upon R will be nothing. It will be equal to delta R upon R. Delta R will be rho L upon A, right? Multiplied by 1.3 square minus 1 upon rho L upon A, right? That is the R. So this rho L upon A, rho L upon A will get cancelled, and we have this factor that's 100 here. We have to multiply it with 100 also, right? So it means that the percentage change in increase is 1.3 square will be actually 1.69, right? It has to be 1.69. So 1.69 minus 1 multiplied by 100, right? So it will be 0.69 multiplied by 100. It has to be equal to 69%, right? It has to be equal to 69%, right? It means that the percentage increase in the resistance for this wire will be actually 69%. So resistance of this wire will actually increase by 69%, right? So 69% is the correct answer for this question. Now there is another similar question. A wire is stretched so that its radius is decreased by, right? Now we are talking about the radius. A wire is stretched so that its radius is decreased by 3%, right? Its radius is actually decreased by 3%. Find percentage change in its resistance. So we'll just proceed in the same fashion or the similar manner for this question as well, right? For this question as well. Let's suppose this is a wire of length L, right? And area of cross section A, right? And area of cross section A will define it as pi r square. It's a circular area of cross section, that's the pi r square, right? And once the radius is decreased by 3%, right? The radius is decreased by 3%, right? If the radius is actually decreased by 3%, find percentage change in its resistance, right? Percentage change in its resistance, right? So we know that initial volume has to be equal to the final volume also, right? Initial volume is actually pi r square multiplied by the length, right? And final volume is actually that's the pi r dash square multiplied the final length. Let me call that as L dash, right? Pi and pi will get cancelled, so it will be r square L, right? R dash square. So it has been decreased by 3%, right? If it is decreased by 3%, it means we are left with 97%, right? We're left with 97%. Or we can say it will be a 0.97 times R, right? 0.97 times R. Or we can write it as 0.97 times R square, right? It will be L dash, right? This is the 97% of the previous value, right? 0.97. So from here, R square and R square will get cancelled. We'll be left with L dash as L upon 0.97 square, right? 0.97 square, right? So this will be the new length, right? If this is the new length, then the new resistance R dash will be actually equal to rho L upon A. Rho is a constant. L is L upon 0.97 square, right? And area of cross section, new area of cross section is actually pi times due area of cross section pi times radius square, that will be 0.97 r square, right? So this is the new resistance, and the initial resistance was rho L upon pi r square, right? Rho L upon pi r square. So delta R will be actually here equal to R dash minus R dash minus R. That is, so it has to be actually rho L upon pi, right? It will be 1 upon 0.97 to the power 4 minus 1, right? And we have R square here, right? So relative change in resistance will be delta R upon R. That will be equal to rho L upon pi R square multiplied by rho L upon pi r square, right? 1 upon 0.97 raised to power 4 minus 1, right? This and this will get cancelled. So we'll be left with fractional change in resistance, that's 1 upon 0.97 to the power 4 minus 1. So this will be the fractional change in resistance, and if we multiply it with 100, we will get the percentage change in resistance. Percentage change in resistance. So this will be the percentage change in resistance, right? So this will be the percentage change in resistance, right? We just multiplied this with 100, we will get the percentage change in resistance, right? So this is the general case for this question that we discussed till now, right? This is one of the general cases for this question. Let's try to solve this general case as well, right? So the case is, if a wire is stretched to n times of its original length, right? Its new resistance will be. So now it's given that this is a wire of length L. Now we have stretched it, right? Area of cross section was A. Now we have stretched it upon stretching. Upon stretching, the length of this wire becomes n times, right? It means the new length L dash will be actually n times L, right? N times L. So volume has to be a constant. So initial volume will be equal to final volume once again. The initial volume was A multiplied by L, right? And the final volume, let's suppose A dash is the new area of cross section and L dash is the new area of new length of this conductor. And the L dash is given as n times L, so it will be n times L into A dash. So from here, A dash comes out to be equal to A upon N, right? A upon N. So this is the A dash, right? That's A upon N. So initial resistance Ri was actually rho L upon A. This was the initial resistance, right? And the final resistance Rf, that's actually equal to rho L dash upon A dash, right? And we can write it as rho times L dash. L dash is n times L upon A dash. A dash is actually A upon N, right? It means our new resistance is rho L upon A multiplied by N square, right? So this is the new resistance, right? So the change in resistance will be delta R. That will be final resistance minus initial resistance, right? That will be equal to rho L upon A times N square minus rho L upon A, right? Or we can write it as okay, we have to find the new resistance, right? We have to find the new resistance only. So we actually calculated the new resistance. This is the new resistance, right? So it means that the new resistance is actually n square times the initial resistance, right? N square times. So the new resistance actually become n square times, or the percentage increase we can write delta R. For delta R, it will be a rho L upon A multiplied by n square minus 1, right? So the percentage increase will be nothing delta R upon R multiplied by 100, right? That will be rho L upon A upon the initial resistance, that was rho L upon A. That's rho L upon A, right? Mul multiplied by n square minus 1 and into 100, right? So this and this will get cancelled again. So the percentage increase in the resistance will be n square minus 1 multiplied by 100, right? So this is the general way of doing it, right? That's n square minus 1 multiplied by 100, right? That's the percentage change in resistance, right? But the new resistance becomes actually n square times the original resistance, right? So it becomes n square times. Now we have question of a galvanometer, right? Question of a galvanometer here. A resistance of a galvanometer is given as, it's actually given as 50 ohms, right? 50 ohms is a resistance of a galvanometer, and its uh, current sensitivity is 1 milliamperes per division, right? And it has 20 divisions, right? So current per division is actually 1 milliampere. Current is actually 1 milliampere per division, right? And number of divisions is given as 20, right? So the total current through the galvanometer, or the range of galvanometer current, will be actually, it will be actually equal to, it has to be equal to Ig, that will be 20 times the current through per division, right? Per division current is 1 milliampere, where we have to multiply it 1 milliampere, that's 1 into 10 to the power minus 3. So this will be actually 2 into 10 to the power minus 2 amperes will be the range. This is the range of galvanometer, right? Range of galvanometer. Range of galvanometer. So up to this range, the galvanometer can measure the current, right? The range of this galvanometer is actually 20 milliamperes, or 2 into 10 to the power minus 2 amperes, right? So the range of this potential difference measurement for this galvanometer will be equal to Ig multiplied by G, where G is the resistance for this galvanometer, right? Right? Ig multiplied by G will be the resistance for this galvanometer, right? So resistance of this galvanometer is 50 ohm. So we'll just multiply it with 50, right? Multiply it with 50. That will be equal to 1 volt. So this is nothing. This is the range of galvanometer. Range of galvanometer for the measurement of what? For the measurement of potential difference. For the measurement of potential difference. Range of galvanometer. Now we have to convert it into a voltmeter of 10 volt, right? It means the range of voltmeter should be, range of voltmeter should be actually 10 volts. Range of voltmeter is given as 10 volts, right? Find the required resistance for the conversion. We have to find the required resistance for the conversion of this galvanometer into voltmeter. And we know that how do we actually convert? How do we actually convert a galvanometer into a voltmeter, right? For conversion, we have this situation like this. This is the galvanometer here, right? Let's suppose this is the galvanometer here, right? This is the galvanometer. And in series with this galvanometer, we actually apply a resistance, right? And this is the external load resistor R, across which we have to measure the potential difference. Let's call this as S, right? Let's call this as S. And across this R, we actually measure the potential difference, right? And we know that some current will come, right? Some amount of current will come, and some current will be through this galvanometer. Let's call that as Ig, and some current will be through this, that will be equal to I minus Ig, right? I minus Ig, right? And this shunt resistance, or this resistance, was calculated as, it was calculated as n minus 1 multiplied by n minus 1 multiplied by G, right? Multiplied by G. So this was the shunt resistance, or the resistance calculated for the conversion of galvanometer into voltmeter. What is this N? N is nothing. N is actually, so N has to be actually the ratio of voltmeter, that's V upon Vg, right? V upon Vg, right? This is the ratio of this. So it has to be equal to 10. It has to be equal to 10. 10, right? V upon Vg will be equal to 10, because V is 10 and the range of volt galvanometer is 1 volt, so 10 upon 1 will be 10, right? So the resistance required for this conversion is 10 minus 1 multiplied by G. G was the resistance of galvanometer, that's 50. So it will be equal to 50 multiplied by 9, that will be equal to 450 ohms. That will be equal to 450 ohms. So the resistance required for the conversion of this galvanometer into voltmeter will be actually 450 ohms. So 450 ohms is the required resistance, right? 450 ohm is the required resistance for this conversion. So let's move on to this question, right? This will be the final question today for this session, right? The question is that find the reading of voltmeter in the given circuit, right? A resistance of voltmeter is given as 1 kilo ohm, right? It's a 1 kilo ohm resistance, right? So resistance of this voltmeter is given as 1 kilo ohm. So we can replace the resistance of this voltmeter by 1 kilo ohm resistance, right? Let's call this as 1 kilo ohm, right? or we can write it as 1000 ohms, right? 1000 ohms. This is 2000 ohm here, right? 2000 ohm here. And there is another resistance, 6000 ohm, right? 6000 ohms. And there is a 1000 ohm here, and they are connected to a cell of EMF 90 volts, right? 90 volt is the EMF of this cell, right? We have to calculate the measurement of this voltmeter, right? How much potential difference is this voltmeter going to measure, right? So what we'll try to do is that we'll just calculate the current through the whole circuit, right? Through the whole circuit. And let's see how the distribution of current will be there, right? So the effective resistance for this circuit will be, for these two resistances, these are in series, so it will be 3000 ohm, and 3000 ohm and 6000 ohm will be in parallel to each other, so their effective resistance will be 3000 multiplied by 6000 upon 9000, right? So it will be actually 1000, it will be actually 2000, right? It will be 2000 ohms, right? 2000 ohms. So effective resistance for these three resistor will be actually 3000 ohms, right? 2000 ohms. We can replace it by 2000 ohm here, right? 2000 ohm. So if this is 2000 ohm is the effective resistance for them, so the final equivalent resistance for this circuit will be actually equal to 3000 ohms, right? 3000 ohms. The current through this circuit will be 90 upon 3000, 90 upon 3000, right? So it will be 3 upon 300, right? 3 upon 100, right? 3 upon 100 ampere will be the current through the circuit, right? So 3 upon 100 ampere will be the current through this circuit, right? So then the potential drop across this 1000 ohm will be, equal to potential difference across this 1000 ohm will be actually equal to 3 upon 100 multiplied by 1000, right? That will be equal to 30 volts, right? That will be equal to 30 volts. So we'll be left with 60 volts, right? We'll be left with 60 volts. So actually how much current was flowing through this? It was 3 upon 100 amperes, right? 3 upon 100 amperes, right? So it's a 1000 ampere, 1000 ampere, right? 1000 ohm voltmeter, right? So it means that there will be two parts of the current here. One part will be going through this, and another part of the current will be going through this, right? The current distribution will be there according to the resistance, right? It will be according to the resistance, right? The most of the current is going to flow through this, right? Because the effective resistance here will be 3000 ohms. So the current through the voltmeter will be actually equal to 3000 upon 6000, right? Multiplied by 3 upon 100, right? That will be upon 2, right? It will be 3 upon 200, right? Amperes. 3 upon 200 ampere will be the current through, not 3, it will be actually 6000 upon 6000 upon 9000, right? 6000 upon 9000 multiplied by 3 upon 100. This will be the current through this voltmeter, right? So it will be actually equal to 18 upon 9, right? 18 upon 900, right? So we can write it as 2 upon 100, right? 2 upon 100, or 1 upon 50 amperes, right? 1 upon 50 amperes. So this much of current will be actually through this voltmeter. So the measurement of this voltmeter will be 1 upon 50 multiplied by the resistance of that voltmeter. That's 1000, right? So it means that this is actually going to measure 20 volts, right? How much? 20 volts. So this voltmeter will actually measure a potential difference of 20 volts through it, right? So 20 volt will be the measurement by this, done by this voltmeter, right? So that's it for today. I will stop here, where we will have to stop here, and we'll be discussing in the next lecture about the magnetism. We'll be starting with the magnetic elements, right? So we'll be starting with Biot-Savart law in the next lecture, right? So let's stop here. Till then, take care and goodbye.